Okay, so here is a laser cut geometric construction set, and you can see it's not faces, but it's edges and vertices, and so we're going to make three-dimensional objects out of these. You see here one of the edge pieces, and you notice that there are hooks on the edge, and the hooks have an orientation, and we'll think about the orientation as going from the base of the hook and pointing in the direction of the hook. So for instance, this piece has a counterclockwise orientation induced by the hooks. And so there's the edge, and here we see a vertex. So here it's a vertex where three edges meet, and so we're going to make a tetrahedron first. So that's the way a tetrahedron works. There's four 4 vertices and 6 edges right here. So let's start out, and we're gonna make sure that we'll give each of these things a clockwise induced orientation. So first of all, as you see, we'll do like this. Put together like so. Like so. Okay, so we've got all the edges on one vertex done now. Okay, keep going with that. So that's all the vertices are connected. So now we just got the final set of edges. Now remember that a tetrahedron has 6 edges and 4 vertices. So you can probably start to see the tetrahedron. And I messed it up. Oops. Put an extra edge there. There we go. So there you see a tetrahedron. Okay, let's go ahead and build a octahedron. And so the octahedron has 6 vertices, which have 4 edges. So the vertex here like a square, and there's 12 edges in total. So we can actually just reuse the edge piece from the tetrahedron. And so let's do a counterclockwise orientation. That's clockwise. You see by our convention of what we mean. And this is counterclockwise. So let's just go ahead and assemble. Okay. So by the nature of the way it works is once we've, for one of these closed surfaces, once we choose a orientation for one piece, that actually then induces an orientation on everything else. And the way that we know that we're not going to paint ourselves into a corner is that, in fact, the geometrical object that's getting built, in this case tetrahedron, which is topological, or octahedron, excuse me, which is topologically the same as a sphere. We know that the sphere is orientable, so we know that this is orientable, so consequently we know that as this building process goes on, that at no particular point are we going to get stuck. And that's because that the first counterclockwise orientation, which it induces the same orientation on all the other pieces. So let's just keep going, finish this up here. Going to get a nice octahedron out of it. It's kind of fun. Okay. And that does it. Now that's an octahedron. You see there with a counterclockwise orientation of the hooks. So this construction set is made out of laser cut chipboard. So chipboard is really awesome because it's really cheap, and also it has a very, what I would say, high resolution for laser cutting. So the parts can be pretty small. And also one nice thing about chipboard is that it's flexible, so that basically you can use that flexibility and elasticity to just provide some cohesive force that keeps the shapes together, and that's a really nice property of the set. So the next thing we want to do is to see how this stuff will go together, because the reason you notice there's some extra hooks that are basically where the faces would be. And so the idea is that those hooks, we can actually connect faces together between these pieces. So for instance, I can take this tetrahedron and connect it with other, say, octahedra and tetrahedra to fill space, because we know that octahedra and tetrahedra can fill space. Now, one thing that we might think about is, why in the heck should these hooks actually enable us to put the stuff together? Because the fact of the matter is that the hooks only go together one way. So how can you close the figure up? Well, the interesting thing is that basically topology tells us that it's okay. So since our surfaces we're building are essentially all orientable, you know that that orientability it essentially induces on each of the polygons that we're using to make it. It induces a direction, and that direction, because of the orientability, cancels out when we put faces together. So that's essentially directly from algebraic topology, and thinking about like orientation of a two-cell induces orientation of the boundaries, and if there's if the whole surface is orientable, then essentially all the boundaries of the various cells making it cancel out. So in this case, what we see is that so this guy I just constructed has a orientability that's clockwise. Now, here's an octahedra I constructed, and in this case, as you can see, that the orientation is counterclockwise, actually. And so let me put that back on. And the thing is that in this case, now, because of these different inherent orientations, I actually can't hook these together. They're actually incompatible. So this is a good example of kind of a chirality thing. So you can't actually hook these together in any way. So, but if I take here now this is another tetrahedron that I constructed, but this actually has a counterclockwise orientation. And so what we see then is that I actually can go like this and go around, and then you see they're now hooked together. and which I think is kind of a fun thing about the construction set. Okay, so let's go ahead. Now we have two octahedra and two tetrahedra, and I just wanted to demonstrate how with this model we can see how octahedra and tetrahedra fill space, and I think that's kind of neat to see. This is I don't really have so many pieces here, so it's not going to be that extensive, but I think this is kind of the minimum system that shows you essentially how it all works. And so let's go ahead and get this other octahedra attached, and it's a little tricky to get some of these connections done, but it's possible. So let's see, let's get this one like that. Kind of, okay. Got two more, that's pretty good. Okay, you see that there it is. That's the way that octahedra and tetrahedra basically pack together to fill space, is that between two octahedra you have these connecting tetrahedra.